Welcome to this video lecture on pump scaling. So the motivation for today's talk is that when you get these pump performance curves from a manufacturer, they're typically only reported for one rotational speed of the pump. So one speed which is driven by the motor. And then also it's not uncommon to see pump curves for just one impeller diameter. But we know from a previous discussion that many times people will put different impellers into the volute casing. And so you'll have a different impeller diameter, maybe you have a different rotational speed, but we don't have the pump performance data for those conditions. So we'll need to do some scaling to figure out how the pump will perform under those conditions. And that's the focus of today's lecture, is really to look at how we do that kind of pump scaling. Before we do that, go ahead and take a look at your screen. And you'll see this picture from the SeaWorld Adventure Park. I thought this was kind of a neat one. This big screw here, and on both sides, these are Archimedes screws. They're just basically, screws that rotate. And they're a type of positive displacement pump. But what they do is they actually carry water from the pool down here up to the top, and I guess it feeds water to the rest of the ride that's going on here. But it's a type of very simple positive displacement pump. It has very low flow rate, very low head rise, but it's very simple. And I just thought this was kind of a neat picture showing such a huge Archimedes screw. I've seen these used in simple irrigation kinds of applications as well. All right, so let's get into the pump scaling work. Oh, I guess before we do that, I have a few links here that I thought were pretty good. These are all concerned how different pumps work. So how does a centrifugal pump work, different types of centrifugal pumps, and then different types of positive displacement pumps. These are more kind of hands-on videos, and I thought they were really well done. So I encourage you to take a look at those when you have an opportunity. All right, so let's talk about pump similarity. So this really kind of goes back to our dimensional analysis approach to analyzing problems. So what we'll start with here is we have the head rise, power, and efficiency of a pump. And we know that those will be functions of the fluid density, fluid dynamic viscosity, the rotational speed of the pump, pump diameter, or the impeller diameter, and the flow rate through the pump. Those are the primary quantities that affect the performance of that pump. And if you go through the dimensional analysis, the Buckingham pi theorem, method of repeating variables, that whole approach, we won't do that here. But if you go through all that, you'll find the following expressions. So here we have what are known as flow coefficients. We have a dimensionless head coefficient, a dimensionless power coefficient, and an efficiency. Efficiency is already dimensionless, so we don't have to make that dimensionless. It's already dimensionless. Those will all be functions of a dimensionless flow rate and the Reynolds number. Okay, and then each of these pi terms is given below here. So here's the dimensionless flow coefficient. I'm sorry, that's the head coefficient. So that's the dimensionless head coefficient. This is the power coefficient. This, of course, is efficiency. Move this down a bit. This is the flow coefficient. And, of course, the Reynolds number. So if we're going to do some scaling of pumps of different, different impeller diameters, maybe different rotational speeds, then these are the important dimensionless parameters related to that. And you'll see that there, in each of these, you have, the gravitational acceleration. Here's the head rise across the pump. Here's the pump rotational speed, the pump impeller diameter. Power is here. Here's the fluid density, flow rate, and then dynamic viscosity there. Okay, and just one other quick thing. It turns out that you can form the efficiency from a combination of these other flow coefficients. So you can also get the efficiency in the following way. It's the dimensionless head coefficient times the flow coefficient divided by the power coefficient. So if you took these dimensionless terms and kind of put them in this format, you'll end up with the efficiency here. So that's just another way to write the efficiency. So you can see very quickly that it's indeed dimensionless because it's formed from other dimensionless quantities. Okay, so here we show that in general, these, the head rise, power, efficiency is a function of flow rate and the Reynolds number. Now, most pumps actually operate at very high Reynolds numbers. And when you get to very high Reynolds numbers, the dependence on Reynolds number becomes less significant. If you recall back from our discussion in pipe flows in the Moody plot, remember in the Moody plot we had the friction factor here, we had a Reynolds number, there was a relative roughness, but we had these curves that look something like this. All right, let me change that curve. We had curves like this, and if you recall, out in this region, we had what was known as a wholly turbulent flow or fully rough zone, something like that. In that region, there was very little dependence on the Reynolds number. You'll notice here that the lines are almost horizontal from the Moody chart. It means that there's very little dependence on the Reynolds number. So the Reynolds number doesn't play much of a role. And we see that also with pumps as well. Once you get to high enough Reynolds numbers, the Reynolds number doesn't play as much of a role. We actually even saw that for the drag coefficient for flow around a sphere, right? Here's a drag coefficient Reynolds number. If you recall that it looks something like this. There was a big region here for the drag coefficient as a function of Reynolds number for flow around a sphere where the Reynolds number just didn't play much of a role. The drag coefficient was nearly constant with Reynolds number. So we tend to see this kind of pattern that at higher Reynolds numbers, the dependence on Reynolds number becomes less important. And it's true for pumps as well. So in this expression here, where we say that these dimensionless coefficients are functions of the flow coefficient Reynolds number, really it's pretty good just to say that the Reynolds number dependence isn't important. Okay? So that instead, these things are a function of the flow coefficient only. Okay, so then if we want to do some scaling, what we need to do, if you remember back from your dimensional analysis work, that we just need to make sure that we keep these dimensionless terms constant from one scale to the other scale, and then we can just do scaling from our pi terms in that manner. So, for example, let's say we have two different geometrically similar flows. So by the way, that this scaling really only, if you'll notice that when we talk about our expressions here, I didn't put in all the geometry for the pump. The only pump geometry part is just the diameter of the impeller. So we're assuming that these are geometrically similar pumps, that they look the same, they're just one's smaller and one's bigger. That's not exactly true, and I'll say more about that later, but if we're assuming that the pumps are actually indeed geometrically similar. But we'll come back to that. So if we keep the dimensionless flow coefficient the same, that means what we need to do is to make sure that, go back up here, we need to make sure that these quantities remain the same between scale 1 and scale 2. And of course, if we do the same thing for the head coefficient, it'll look like this. We're going to refer back to these relations that I'm writing now in just a moment. So here's the dimensionless power coefficient. Just make sure I've got those right. Okay. And since if we can hold these constant, between scale 1 and scale 2, then we know just because the efficiency can be written in terms of those coefficients, then we'll know that the efficiencies will be the same, if that's true. Now we're going to consider a couple of cases. One where we change the pump speed and one where we change the impeller diameter. So let's first start where we change the impeller speed. Okay, so case 1. those are really the two cases that we come across: is changing the speed of the motor, which changes the impeller rotational speed, or just changing the impeller diameter that's in the volute casing. So in this case, the the diameter will be constant, and omega varies. So if that's the case, then this first quantity, just based on the flow coefficient, the d's will cancel out, and then you'll just have Q1 over Q2 is equal to omega 1 over omega 2. And then you'll have from the headrise coefficient, we'll assume that the g's are the same, same Earth gravity, right? And again, the d's are the same, so those disappear. So then you'll have h1 over h2 is omega 1 over omega 2. That whole thing is squared. And then for the power terms, you'll have power 1 over power 2 is equal to omega 1 over omega 2, that whole thing cubed. And here, I'm assuming that the densities are the same. It's the same fluid that you're pumping. You're just only changing the rotational speed of the pump. And then, again, the efficiencies will be more or less constant in that particular case. So that's how you would do scaling when you're dealing with changes in rotational speed. It's fairly straightforward. You would know from your manufacturer what the pump performance curve is for a particular rotation speed. And then, knowing at a given flow rate and head rise what you have, and you wanted to change to a different rotational speed, you can scale to find out what your new flow rate, new head rise, new power will be under those new conditions, just by using these relations. And it works pretty well for changing rotational speed. Okay, now let's do the other case, case 2, where we hold omega constant and d varies. So in that case, what we'll have is Q1 over Q2 is equal to d1 over d2 cubed. H1 over H2. What I'm doing now is just going back up to these relations, holding, like, for example, this one, the G constant and the omega constant. Now we're on to the powers. Okay, now we have these expressions. So again, if we keep the rotational, we have from the manufacturer our pump performance curve for a particular single impeller and a particular rotational speed, but now we're going to replace that impeller with one of a different size. And so this would be a way to predict the performance using that new impeller for the same rotational speed. Now, the prediction using this is not all that great. I mean, it's okay. It's good enough for a back of the envelope calculation, but it's not that great. And the reason for that is because we're not really keeping geometric similarity when we change the pump impeller. Typically what's done is the volute casing is the same, so that remains the same, and all we do is replace the impeller. So it's not geometrically similar. If it was geometrically similar, if we put in a smaller impeller, we should make the whole pump smaller. And really, if you're going to be very detailed about it, you'd even have to change the surface roughness of the interior of the pump to scale that in the same way. It's just not practical to do that. So instead, we violate geometric similarity and keep the volute casing and all the roughnesses the same and only change the pump impeller. And because we're not maintaining geometric similarity, we can't expect the scaling to be perfect. And it's not. Okay, so these expressions I have here are really just at best approximate. And I'll do an example where you can see just, how well they work. But it's not, it's not great. So people have come up instead with other kind of empirically based scalings. So things that might work a little better, but they're not based on any theoretical analysis. They just come from a lot of experimental data and experience. So we'll just say this is a better empirical set let me write set of scaling relations. Okay, so again, these come just from just trying to do a better job by just basically curve fitting data. So you'll see here, just from dimensional analysis, we get the ratio of diameters cubed, but from some experimental scaling, it turns out it works better if you just square it rather than cube it. And then for the head rise, that one stays about the same. It's just d1 over d2 squared still. And for the power, instead of going to the fifth, raising it to the fourth seems to work better. So you can see that the difference really is just coming in here, in here. And that new set of scaling seems to work better. Again, it just comes from, rather than dimensional analysis, it really just comes from some experimental data. And then a better approximation for the efficiency, again, because we're not doing perfect geometric scaling, the efficiencies won't match up that well. But if you wanted to scale the efficiencies, this empirically based scaling seems to work relatively well. So here's your starting efficiency that you're dealing with that pump impeller, and then here's the efficiency with that new impeller diameter. So again, that's based on some empirical scaling. Okay, so that gives us a way to do scaling when you're changing the pump impeller speed. We can use this, and that works pretty well. And then when we're changing the pump impeller diameter, you can use this coming from dimensional analysis. It's okay. It's not great because of violating geometric similarity. Or you can use this more empirically based set of scaling rules. That works better. Okay. All right. I have one more thing I wanted to talk about. And this is just a plot showing you what kind of pump model number would be most effective for your particular application. So, you know, many companies, they'll make more than one type of pump. They make a whole bunch of different models of pumps for different applications. And it's helpful to be able to figure out, which model numbers are most appropriate for your given application. It'd be nice to be able to narrow it down. Now, the first thing you could do is to look at the specific speed. So that's covered in a different lecture, but specific speed will tell you what type of pump is most efficient for your particular application. You just need to know the flow rate, the head rise, and the rotational speed for your application. If you know that, you can calculate specific speed, and that there's a plot that will show you what kind of pump would be most effective, whether it be an axial flow pump, a mixed flow pump, or a radial style flow pump. So let's say you do that calculation and you find out, okay, a radial flow pump is most effective. It would be most efficient, I should say. And then you go to a company's website and they make many different kinds of centrifugal pumps, radial flow style pumps. And you need to determine from all these different model numbers what kind of centrifugal pump would be best for your application. So what companies do is they'll provide this kind of a plot that shows different model numbers. You can see here that are most appropriate for a given volumetric flow rate and head rise for your application. And then this is at a specific rotational speed. So a lot of companies will have these kind of plots. So for example, if I had a volumetric flow rate of, let's say, 400 gallons per minute and a head rise of 300 feet, so I would be right at this point, then that would mean, that kind of pump model number from this manufacturer is the most appropriate pump I could use for this application. Just gives you a really quick way to narrow down what model number for a particular manufacturer is most appropriate for your application. And in this particular case, the numbering scheme here for this company, they give it here. So this first number is just the discharge line side. That's the outgoing pipe diameter, basically. Pump model AE, it's just within their own numbering scheme within their own company. And 12 is the maximum diameter of impeller in inches. So again, we just talked about being able to put impellers of different diameters into the into the volute casing. So this would be the maximum diameter in inches for that particular one. So anyway, I just wanted to show you how these kind of plots work because you'll see them frequently for different pump manufacturers. Okay, I guess I had one other item here. Let's see what I want. Oh yeah, this set of plots is just another set of kind of pump performance plots I wanted to show just from coming from a different manufacturer. This one is just the head rise as a function of volumetric flow rate. We've seen this kind of plot before. There should be no surprises here. And I wanted to show you, just to emphasize that these different curves here that you're seeing with the different numbers, these all correspond to the different impeller diameters in this particular pump's volute casing. So you can see they actually have, what, 1, 2, 3, 4, 5, 6, 7 different impellers you could fit into this one volute casing. So I just wanted to emphasize the point that changing out impeller diameters is not uncommon. The red lines here you can ignore. That's something else. So don't worry about the red stuff. Down here is showing the brake horsepower for the pump. A lot of times, I think I've shown you in a previous lecture that on this kind of a plot, the dark lines are the head rise as a function of volumetric flow rate. These kind of contour lines here correspond to the efficiency of the pump. And in a previous lecture, I showed some dashed lines that showed the brake horsepower on that same plot. Here, this manufacturer puts the power consumption just on a different plot altogether. And again, showing the power consumption as a function of flow rate. So this would be your power versus flow rate. And these are for your different impeller diameters. Okay. Just again, trying to emphasize that we're dealing with different, that we can have different impeller diameters. The last plot here is net positive suction head, which we haven't covered yet. This is actually required net positive suction head versus volumetric flow rate. So we'll talk about that in a different lecture. But the one thing I wanted to emphasize here is, again, you see the different impeller diameters, but you don't have all the lines. NPSHR is a weaker function of the impeller diameter. It still plays a role, but it's not as strong of a role as you can see up here, for example, with the head rise. So when we talk about NPSHR, again, in a different lecture, just try to keep in mind that if we switch out the impeller diameters, it'll have some effect, but not a huge effect. Okay? All right, there I think I've covered everything I wanted to for this lecture.